Every grandparent knows this. The hug from your grandchild does not feel like any other hug. Nothing like a friend's embrace or your partner's arms. Something about holding that small body reaches a place that other physical contact does not touch. A depth of settling, a quality of rightness, a warmth that seems to come from somewhere beneath the skin. You have attributed this to love, to the bond you share, to the particular softness of a child's body pressed against yours. Every explanation you have offered yourself is emotional. The explanation is molecular. Your immune system identifies the child before your conscious mind has processed who you are holding. Volatile compounds on the child's skin, molecules linked to the major histocompatibility complex, the genetic system that determines organ transplant compatibility, reach your olfactory epithelium within the first second of contact. Your body knows who it is holding before your brain has formed a thought about it. The recognition is chemical. The response is hormonal. The oxytocin your hypothalamus releases when you hold your grandchild is measurably higher than the oxytocin it releases when you hold anyone else. Same duration, same pressure, same surface area of contact. The hug feels different because the dose is different. The dose is different because the molecular identification is different. The molecular identification is different. The identification is genetic. Think about what your immune system is actually doing during that first inhalation. Because the molecular recognition system operating in your nose is the system that determines whether a transplanted organ will be accepted or rejected, repurposed for a function no transplant surgeon discusses. Major histocompatibility complex, MHC, called HLA in humans, is a cluster of genes on chromosome 6 that encodes the surface proteins your immune system uses to distinguish self from non-self. Every cell in your body displays MHC proteins on its surface, molecular identity tags that your immune cells inspect continuously. When a transplanted organ carries MHC proteins that differ from yours, your immune system identifies those proteins as foreign and attacks. Rejection is an MHC event. Compatibility is an MHC match. The system exists to identify what belongs to your body and what does not. But MHC genes also produce something else, volatile organic compounds, small molecules secreted in sweat, sebum, and the oils your skin produces continuously. These volatiles create a genetically determined scent signature that is nearly unique to each individual. Your MHC profile produces a body chemistry that smells subtly but measurably different from anyone with a different MHC profile. Your nose can detect these differences. Watkins T-shirt studies at the University of Bern demonstrated that humans reliably distinguish between MHC similar and MHC dissimilar individuals by scent alone, preferring dissimilar MHC for mate selection, but preferring similar MHC for kin recognition. Your grandchild shares a portion of your MHC profile. You passed half your MHC genes to your children. Your children passed half of their MHC genes, including some of yours, to your grandchildren. The recombination means your grandchild does not carry your exact MHC profile. The combination is new, mixed with the other grandparent's contribution. But enough overlap remains for your olfactory system to detect the genetic similarity. The volatile compounds on your grandchild's skin carry molecular signatures that overlap with your own MHC-determined scent profile, and your nose is calibrated to detect that overlap. Calibration appears to have a genetic component. The MHC genes that produce your scent profile also influence which scent profiles your olfactory receptors respond to most strongly. But early life exposure to family members' scent signatures may also shape the system. The nose calibrating to the specific MHC volatiles present in the household during infancy and childhood. Whether the tuning is entirely hardwired or partly shaped by developmental exposure is not fully resolved. The functional result is unchanged. Your nose responds preferentially to scent profiles that share components of your own, and the recognition operates below conscious awareness. You see, the recognition happens in the first breath. Volatile compounds from the child's skin and scalp enter your nose during the first inhalation of the embrace, within the first 1 to 2 seconds of contact. They bind to olfactory receptor neurons in the epithelium. the patch of tissue at the top of each nasal cavity containing roughly 10 million receptor neurons. But here, the signal does not route to the digestive system. It routes to the amygdala and the hypothalamus through the direct olfactory limbic pathway, bypassing the thalamus, bypassing conscious processing, arriving at the emotional and hormonal centers of the brain before you have registered the scent as a scent. You do not smell your grandchild and then feel something. Your limbic system responds to the molecular signature and then you feel something. The sequence is chemical first, emotional second. The emotion you attribute to love is downstream of a molecular event you never perceived. And here is what the limbic system does with that molecular recognition. Because the oxytocin response to kin contact differs from the oxytocin response to any other contact, and the difference is what makes the hug feel like no other hug you receive. Oxytocin, the neuropeptide released during physical contact, social bonding, and trust, is not released in equal amounts during all embraces. The magnitude of the release is modulated by who you are touching. Feldman and colleagues measured oxytocin during contact across relationship types: parent-infant, romantic partner, friend, stranger. Kin contact produced significantly higher oxytocin than non-kin contact at comparable physical parameters. Not marginally higher, not within the range of normal variation, but significantly elevated in a way that the physical contact alone could not explain. Whether the elevation is driven by genetic recognition specifically, by attachment history, or by both operating together has not been fully isolated. But the magnitude of the difference between kin and non-kin contact is consistent and significant across the studies. Hypothalamic paraventricular nucleus, the brain region that produces and releases oxytocin, receives the MHC recognition signal from the olfactory limbic pathway and amplifies its output. The amplification is conditional. Touch alone produces a baseline oxytocin response. Any embrace, any sustained physical contact activates the paraventricular nucleus and releases oxytocin. But when the olfactory limbic pathway simultaneously reports genetic relatedness through MHC volatile recognition, the paraventricular nucleus increases its output beyond the baseline. The two signals, somatosensory input from the touch, olfactory input from the MHC volatiles, converge on a single nucleus and produce a combined response that exceeds what either signal would produce alone. Your body does not just release oxytocin because skin is touching skin. It releases more oxytocin because the skin it is touching belongs to your genetic continuation. And the olfactory system has confirmed this before your conscious mind has registered the scent. The hug feels deeper because the hormonal response is larger. The hormonal response is larger because the molecular identification confirmed genetic relatedness. The warmth you feel is not just emotion. It is a measurably higher concentration of oxytocin in your bloodstream, a concentration that non-kin contact at identical physical parameters does not produce. Every grandparent who has said, "There is nothing like holding my grandchild," was reporting a pharmacological fact without knowing it. The nothing like it quality is a dose difference. The dose difference is a molecular recognition event. Now, a second question opens. Because the molecular recognition and the oxytocin differential explain why the hug feels emotionally different, why the warmth is deeper, why the comfort is more complete, why the bond feels like it operates at a level words cannot reach. They do not explain why the hug feels physically different, why the sensation in your chest is different, why the settling in your body is different, why the physical quality of holding a grandchild is unlike the physical quality of holding a friend or a partner or a colleague. You have felt this physical difference, the way the child's body fits against yours, the way your breathing changes, the way something in your chest shifts and quiets within seconds of the child pressing close. The emotional difference has a molecular explanation. MHC recognition, amplifying oxytocin release. The physical difference has a physics explanation, and the physics involves your heart doing something it does not do for anyone else. Feldman's research on physiological synchrony documented cardiac entrainment in mother-infant dyads, two hearts beating in phase within seconds of sustained chest-to-chest contact. The mechanism was measured in mothers holding their infants during face-to-face interaction. The finding has not been replicated specifically in grandparent-grandchild pairs, but the mechanism is vagal, not relationship-specific. The same ventral vagal complex, the same mechanoreceptor to cardiac feedback loop, the same chest wall vibration transmission that produced entrainment in mother-infant pairs, operates in any sustained chest-to-chest embrace between bonded individuals. When you hold your grandchild close enough that your chests touch, the anatomy predicts what Feldman measured in a different dyad, two separate hearts, yours and the child's, locking into phase alignment through a mechanism that operates entirely below conscious awareness. Mechanism is vagal. Mutual physical contact activates Porges' ventral vagal complex, the social engagement system, in both you and the child simultaneously. Your vagal output to your heart is modulated by the somatosensory input from the child's body. The rhythm of the child's heartbeat, transmitted through the chest wall during close embrace, is detected by mechanoreceptors in your chest and feeds back into your vagal cardiac control loop. Your heart adjusts. The child's vagal system performs the identical computation in reverse, detecting your heartbeat through the chest wall, adjusting the child's cardiac rhythm toward yours. Two hearts converge. The child's rate slows slightly toward yours, the faster, younger heart decelerating. Yours adjusts slightly toward theirs, the slower, older heart finding a compromised frequency. Within seconds, the rhythms are synchronized. Two cardiac oscillators, coupled through mechanical vibration, transmitted across the contact surface where your chests meet. You have felt this without knowing what it was. The moment in the hug when something shifts, when the embrace stops being two bodies pressing together and starts feeling like one organism settling. That shift is the entrainment locking in. The child's heart has found yours. Yours has found theirs. The vagal system in both bodies has established a coupling, and the sensation of settling, of the hug deepening without either of you moving, is the cardiovascular synchronization arriving at phase lock. Entrainment is documented most robustly in caregiver-infant dyads with established bonds. The genetic component versus the attachment component has not been fully separated in the synchrony literature. What is established, the ventral vagal system responds more robustly to bonded kin contact than to stranger contact, and the settling you feel when you hold your grandchild close, the deep physical quieting that seems to reach into your chest rather than staying on the surface of your skin, is your cardiovascular system confirming what your olfactory system already identified. Your heart is synchronizing with the heart of your genetic continuation. The depth of the feeling is the depth of the coupling. That convergence, your heart locking into phase with a heart 50 or 60 years younger, through vagal feedback mediated by chest wall mechanoreceptors, is the detail that placed the grandchild's hug in the cardiovascular physiology literature for me. Not metaphorically, not poetically, as a measurable cardiac coupling event between two bonded organisms whose vagal systems recognize each other through contact. The mother cell's discussion described this synchrony from the infant's perspective, the child's autonomic system calibrating to the caregiver's rhythms as one of the hidden regulators that maintain physiological stability. What you experience when you hold your grandchild is the reciprocal event, the older heart finding the younger one through the identical vagal mechanism decades later. Physical difference has a thermal dimension. Your body detects without your awareness. Children run warmer than adults. Core body temperature in children under 10 averages 37 to 37.5 degrees Celsius, slightly higher than the adult average of 36.5 to 37. Skin surface temperature is correspondingly elevated. The child's forehead, cheeks, neck, and arms run warmer to the touch than an adult's. When you hold your grandchild, a temperature differential of 1 to 2 degrees exists across the entire contact surface. The child's skin is measurably warmer than yours. This differential activates TRPV warmth receptors in your skin, molecular thermoreceptors that detect temperature changes across the skin surface and report them to the somatosensory cortex. The warmth from the child's body is a thermal input that your skin does not receive from same-age adults whose skin temperature matches or falls below yours. When you hug a friend, a partner, a sibling of similar age, the temperature gradient across the contact surface is negligible. Both bodies are at similar temperatures, no net thermal signal is generated, your TRPV receptors are not preferentially activated. When you hold your grandchild, the gradient is present and sustained, 1 to 2 degrees warmer across every square centimeter of contact for the duration of the embrace. Your somatosensory cortex processes this warmth as a specific quality of contact that adult embraces do not produce. A felt warmth, a radiating quality, a sense that the child is giving off heat in a way that other people do not. Child literally feels warmer against your skin. The warmth is not imagined. It is not metaphorical. It is not the warmth of love projected onto a neutral thermal signal. It is a 1 to 2 degree temperature differential detected by molecular thermoreceptors in your skin and processed by your somatosensory cortex as a physical quality of the embrace that no adult contact replicates. The reason your grandchild feels warmer than anyone else you hold is that your grandchild is warmer than anyone else you hold, and your skin has the molecular machinery to detect the difference. Well, and the geometry matters. Because the body size difference between you and your grandchild produces a contact pattern that adult embraces cannot replicate. And the mechanoreceptor physics of that pattern explains why the hug feels more complete, more total, more enveloping than any adult hug you receive. Grandchild's body is small enough that your arms fully enclose the torso. The embrace is geometrically complete. Your hands reach beyond the child's back. Your arms wrap around the full circumference of the child's ribcage. The child's body is fully contained within your arm span. Your hands may overlap on the far side. Your forearms may press against each other behind the child's back. The child's entire torso, front, sides, and back, is in contact with your body or your arms. When you hug another adult, the geometry is different. Your arms reach partway around a same-sized torso, your hands touch the other person's back but do not overlap, the contact is partial, the far side of their torso is untouched. The embrace is geometrically open. Something is missing from the contact pattern that the somatosensory cortex detects as incompleteness. Full enclosure activates mechanoreceptors across a dramatically larger contact surface. The entire inner surface of both arms from shoulder to wrist, your full chest, your upper abdomen, sometimes your chin and cheeks pressing against the top of the child's head. Your somatosensory cortex receives bilateral full arm and full torso input simultaneously. Every Ruffini ending, every Merkel cell, every Pacinian corpuscle across the entire anterior contact surface firing at once. The cortical map of the hug is significantly larger and more complete than the partial map an adult embrace produces. More mechanoreceptor activation means a larger cortical representation. Your brain processes the contact as more complete because the somatosensory input is more complete. The felt difference between holding a grandchild and hugging an adult is partly a difference in how much of your somatosensory cortex is simultaneously active. And the full enclosure geometry of the child's small body produces a cortical map that no adult body can generate because no adult body is small enough for your arms to fully enclose. Chest weight discussion described distributed pressure activating vagal pathways through mechanoreceptor input to the brainstem. The grandchild's hug operates through identical physics, but reciprocally. Your arms provide distributed pressure around the child's torso, activating the child's vagal pathways through an identical mechanoreceptor to brainstem root. But the child's body also provides distributed pressure against your chest, the child's weight, the child's arms wrapping around your neck or your torso, the child's head resting against your collarbone or your torso, the child's head resting against your collarbone or your sternum. You receive the deep pressure signal from the child's body, the vagal activating distributed compression that the weighted blanket delivers through inert mass, delivered here through a warm, breathing, genetically recognized body whose heartbeat you can feel through the chest wall and whose MHC volatiles you're inhaling with every breath. And then, the persistence. Because the hug does not end when you let go, the molecular physics explains why the feeling lasts after the child has left the room, and why holding the child's sweater to your face produces a shadow of the original response hours later. Oxytocin has a plasma half-life of approximately 3 to 5 minutes. The molecule itself is cleared from the blood within minutes. But its effects on neural circuitry persist for 20 to 60 minutes after release. The receptors it bound continue to modulate the neurons they influence long after the oxytocin molecule has been metabolized. The post-hug calm. The warm, settled feeling that remains long after your grandchild has left the room is the downstream effect of the elevated oxytocin continuing to modulate neural activity in 3 areas simultaneously. The amygdala, where it reduces anxiety and threat detection, making the world feel safer and quieter. The nucleus accumbens, where it sustains the reward signal that the embrace initiated, maintaining the sense of well-being, and the hypothalamus, where it maintains the parasympathetic bias the vagal coupling produced, keeping your heart rate lower and your breathing slower than it was before the hug. Calm is not memory. It is not nostalgia arriving minutes after the child is gone. It is active neurochemistry, oxytocin-bound receptors continuing to shift neural activity toward rest, toward safety, toward the parasympathetic state the embrace produced. If you feel better for hours after seeing your grandchildren, you are experiencing a pharmacological effect, a sustained neuromodulatory shift produced by kin-specific oxytocin release at concentrations that non-kin contact does not achieve. But the persistence extends beyond the oxytocin half-life, and the reason is olfactory. And this is where the molecular recognition system reveals something that most grandparents have experienced but never had explained. MHC volatile compounds from the child's skin persist on your clothing and your own skin for hours after contact. Each subsequent inhalation of the residual scent, below your conscious detection threshold, invisible to your awareness, unregistered by your cortex as a smell, reactivates the olfactory limbic pathway that recognized the child during the embrace. Your body continues receiving kin recognition signals long after the child is gone. The amygdala continues responding to the molecular trace. The hypothalamus continues releasing low levels of oxytocin in response to the limbic activation. The feeling that the child is somehow still present, that the hug lingers in a way other hugs do not, is your olfactory system detecting molecular traces of the child's MHC signature on your own skin and clothing, and your limbic system responding with continued oxytocin release that your conscious mind attributes to memory, but your olfactory system knows is a current sensory event. Grandparent who holds a grandchild's sweater to their face after the child has gone home, who buries their nose in the fabric and breathes, is not being sentimental. The sweater smells like the child because the child's MHC profile is encoded in the volatile compounds absorbed by the fibers. The comfort lasts because the molecule persists. The urge to hold the sweater close is the body seeking the molecular input that produced the oxytocin the brain has been receiving all afternoon and has now lost. That connection, the molecular trace of your grandchild persisting on fabric and skin, reactivating the kin recognition pathway hours after the embrace ended, producing continued oxytocin release from a scent you cannot consciously detect, is the finding that made the post-visit sadness look less like emotion and more like a withdrawal from a molecular signal the body had been receiving and lost. Hold your grandchild. Hold them the way your body already knows to hold them, close, full, chest to chest. Your arms know to wrap fully. The mechanoreceptor system produces its maximum cortical activation from full enclosure. Your nose knows to breathe near the scalp. The scalp where the sebaceous glands produce the highest concentration of MHC-linked volatiles, where the molecular identity signal is strongest. Your chest knows to press close. The contact surface where the mechanoreceptors detect the child's heartbeat, and the vagal system begins the cardiac synchronization that produces the settling you feel. 20 seconds minimum. The threshold research identifies for significant oxytocin release, amplified here by the MHC-mediated kin recognition that non-kin contact does not trigger. Do not rush the embrace. The cardiac entrainment requires seconds to lock in. The vagal coupling needs sustained chest wall contact to establish the feedback loop. The MHC recognition occurs in the first breath, but the oxytocin response builds over the first 20 to 30 seconds as the hypothalamus sustains its output. The want detection is immediate. The TRPV receptors fire on contact. But the somatosensory integration of the full enclosure pattern requires sustained input for the cortical map to reach its complete representation. Every second of sustained contact deepens the physiological response. The hug that lasts 5 seconds delivers a fraction of what the hug that lasts 30 seconds produces. Embrace is bidirectional. Your grandchild is receiving the reciprocal signal. Their vagal system is coupling with yours. Their oxytocin is rising. Their body recognizes yours through the molecular system their own MHC genes provide. You are not just holding them, they are holding you. Both bodies are performing mutual molecular recognition, mutual cardiac synchronization, mutual vagal activation, mutual oxytocin release. 2 million years of primate caregiving calibrated every parameter of this interaction. The arm position, the breathing pattern, the chest-to-chest orientation, the duration. Trust the calibration. Hold. The hug you give your grandchild differs from every other hug you give. Your olfactory system identifies the child's genetic signature within the first breath. Volatile compounds from the child's MHC profile binding to olfactory receptor neurons and routing through the limbic pathway to the amygdala and hypothalamus before your cortex has registered the embrace. Your hypothalamus releases oxytocin at a magnitude reserved for kin, the paraventricular nucleus amplifying its output in response to the combined somatosensory and olfactory signals that only bonded kin contact produces. Your heart synchronizes with the child's heart through vagal coupling within seconds, 2 cardiac oscillators locking into phase through mechanoreceptor feedback across the chest wall. Your arms fully enclose the small body, producing a bilateral full-surface mechanoreceptor activation pattern that no adult embrace replicates. The somatosensory cortex mapping a contact area that adult geometry cannot produce. And when the child leaves, their molecular signature remains on your skin and clothing, reactivating the kin recognition pathway with every breath you take near the fabric, producing continued oxytocin release from a scent below your conscious detection threshold, sustaining the parasympathetic state the embrace produced, making the hug linger in a way that other contact does not. The grandparent who lives far from the grandchild, who sees them twice a year, who measures the intervals between visits in weeks and months, carries a body that was calibrated by 2 million years of primate evolution to hold its genetic continuation regularly. The MHC recognition system, the oxytocin amplification, the cardiac entrainment, the full enclosure geometry, every mechanism described in this discussion was designed by selection pressure to operate frequently, to be reinforced by daily contact, to maintain the physiological bond between caregiver and young through sustained proximity. The grandparent who lives at a distance is maintaining a molecular recognition system that receives its input twice a year. The post-visit sadness is real. The ache is real. The body is not being sentimental. The body is experiencing the withdrawal of a molecular signal it was built to receive continuously and now receives in intervals that the physiology was never designed for. A note on adoption. Because the grandparent of an adopted grandchild may wonder whether the molecular recognition applies. The MHC-mediated genetic kin recognition requires shared MHC profiles, and an adopted grandchild does not share MHC genes with the adoptive grandparent. The olfactory limbic recognition of genetic relatedness through volatile compounds would not operate through MHC matching. But the olfactory system also calibrates the familiar scent through repeated exposure. The grandparent's nose learns the specific scent of the child over months and years of contact, and the limbic system assigns emotional significance to that scent through associative learning rather than through genetic matching. The cardiac entrainment operates through vagal coupling during physical contact, and vagal coupling does not require genetic relatedness. The thermal physics operates through temperature differential, and all children run warmer than older adults regardless of genetic relationship. The full enclosure geometry operates through body size, and all small children fit within a grandparent's arms regardless of genetics. The MHC component is absent. The cardiac, thermal, mechanoreceptor, and learned olfactory components are fully present. The hug feels different because most of the physics operates through contact and proximity rather than through genetics. And the contact is what the grandparent provides. Every grandparent knows this. The hug is different. Now you know why. And the knowing does not diminish the feeling. The feeling is the molecular recognition, the hormonal amplification, the cardiac coupling, and the mechanoreceptor activation converging on a single event that your body identifies as the most important physical contact it can receive. The physics does not replace the love. The physics is what the love is made of. Measured in volatile compounds and oxytocin concentrations and cardiac phase alignment and mechanoreceptor activation patterns. Neither diminishes the other. Both are real. Hold.